In computer science, merge sort is an O, and log n, comparison-based sorting algorithm. Most implementations produce a stable sort, which means that the implementation preserves the input order of equal elements in the sorted output. Merge sort is a divide-and-conquer algorithm that was invented by John von Neumann in 1945. A detailed description and analysis of bottom-up merge sort appeared in a report by Goldstine and Neumann as early as 1948. Algorithm. Conceptually, a merge sort works as follows: divide the unsorted list into n sublists, each containing one element. Repeatedly merge sublists to produce new sorted sublists until there is only one sublist remaining. This will be the sorted list. Top-down implementation. Example: C-like code using indices for top-down merge sort algorithm that recursively splits the list into sublists until sublist size is 1, then merges those sublists to produce a sorted list. The copy-back step could be avoided if the recursion alternated between two functions so that the direction of the merge corresponds with the level of recursion. Bottom-up implementation. Example code for C using indices for bottom-up merge sort algorithm which treats the list as an array of n sublists of size 1, and iteratively merges sublists back and forth between two buffers. Top-down implementation using lists. Pseudocode for top-down merge sort algorithm which recursively divides the input list into smaller sublists until the sublists are trivially sorted, and then merges the sublists while returning up the call chain. Function merge sort. List M, base case. A list of 0 or 1 elements is sorted, by definition. If length, M, equals 1, return M. Recursive case. First, divide the list into equal-sized sublists. Var list left, right, var integer middle equals length, M, /2, for each x in M before middle, add x to left, for each x in M after or equal middle, add x to right. Recursively sort both sublists. Left equals merge sort, left, right equals merge sort, right, conquer merge the now sorted sublists. Return merge, left, right. In this example, the merge function merges the left and right sublists. Function merge, left, right, var list result, assign the element of the sublists to result variable until there is no element to merge. While length, left, 0 or length, right, 0, if length, left, 0 and length, right, 0, compare the first two element, which is the small one, of each two sublists. If first, left, equals first, right, append first, left, to result, left equals rest, left, else, append first, right, to result, right equals rest, right, else if length, left, 0, append first, left, to result, left equals rest, left, else if length, right, 0, append first, right, to result, right equals rest, right, end while, return result. Natural merge sort. A natural merge sort is similar to a bottom-up merge sort except that any naturally occurring runs in the input are exploited. In the bottom-up merge sort, the starting point assumes each run is one item long. In practice, random input data will have many short runs that just happen to be sorted. In the typical case, the natural merge sort may not need as many passes because there are fewer runs to merge. In the best case, the inputs is already sorted, so the natural merge sort need only make one pass through the data. Example: start 3, 4, 2, 1, 7, 5, 8, 9, 0, 6, select runs, 3, 4 2 1, 7 5, 8, 9 0, 6, merge 2, 3, 4 1, 5, 7, 8, 9 0, 6, merge 1, 2, 3, 4, 5, 7, 8, 9 0, 6, merge 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Tournament replacement selection sorts are used to gather the initial runs for external sorting algorithms. Analysis. In sorting n objects, merge sort has an average and worst case performance of O, now log O n. If the running time of merge sort for a list of length n is t, n, then the recurrence t, n, equals 2t, n/2, plus n follows from the definition of the algorithm. The closed form follows from the master theorem. In the worst case, the number of comparisons merge sort makes is equal to or slightly smaller than, which is between and. For large n and a randomly ordered input list, merge sort's expected number of comparisons approaches I plus or minus an fewer than the worst case where, in the worst case, merge sort does about 39% fewer comparisons than quicksort does in the average case. In terms of moves, merge sort's worst case complexity is O, now log n, the same complexity as quicksort's best case, and merge sort's best case takes about half as many iterations as the worst case. Merge sort is more efficient than quicksort for some types of lists if the data to be sorted can only be efficiently accessed sequentially, and is thus popular in languages such as Lisp, where sequentially accessed data structures are very common. Unlike some implementations of quicksort, merge sort is a stable sort as long as the merge operation is implemented properly. Merge sort's most common implementation does not sort in place. Therefore, the memory size of the input must be allocated for the sorted output to be stored in. Merge sort also has some demerits. One is its use of two n locations. The additional n locations are commonly used because merging two sorted sets in place is more complicated and would need more comparisons and move operations. But despite the use of this space, the algorithm still does a lot of work. The contents of M are first copied into left and right and later into the list result on each invocation of merge sort. Variants of merge sort are primarily concerned with reducing the space complexity and the cost of copying. A simple alternative for reducing the space overhead to n/2 is to maintain left and right as a combined structure, copy only the left part of M into temporary space, and to direct the merge routine to place the merged output into M. With this version it is better to allocate the temporary space outside the merge routine, so that only one allocation is needed. The excessive copying mentioned previously is also mitigated, since the last pair of lines before the return result statement becomes superfluous. In-place sorting is possible, and still stable, but is more complicated, and slightly slower, requiring non-linear arithmetic quasi-linear time O, now log 2an. One way to sort in place is to merge the blocks recursively. Like the standard merge sort, in-place merge sort is also a stable sort. Stable sorting of linked lists is simpler. In this case the algorithm does not use more space than that already used by the list representation, but the O, log, k used for the recursion trace. An alternative to reduce the copying into multiple lists is to associate a new field of information with each key. This field will be used to link the keys and any associated information together in a sorted list. Then the merging of the sorted lists proceeds by changing the link values. No records need to be moved at all. A field which contains only a link will generally be smaller than an entire record, so less space will also be used. This is a standard sorting technique, not restricted to merge sort. Use with tape drives. An external merge sort is practical to run using disk or tape drives when the data to be sorted is too large to fit into memory. External sorting explains how merge sort is implemented with disk drives. A typical tape drive sort uses 4 tape drives. All I/O is sequential. A minimal implementation can get by with just 2 record buffers and a few program variables. Naming the 4 tape drives as A, B, C, D, with the original data on A, and using only 2 record buffers, the algorithm is similar to bottom-up implementation, using pairs of tape drives instead of arrays in memory. The basic algorithm can be described as follows: merge pairs of records from A. Writing 2 record sublists alternately to C and D, merge 2 record sublists from C and D into 4 record sublists. Writing these alternately to A and B, merge 4 record sublists from A and B into 8 record sublists. Writing these alternately to C and D, repeat until you have one list containing all the data, sorted in log 2, n, passes. Instead of starting with very short runs, usually a hybrid algorithm is used, where the initial pass will read many records into memory, do an internal sort to create a long run, and then distribute those long runs onto the output set. The step avoids many early passes. For example, an internal sort of 1024 records will save 9 passes. The internal sort is often large because it has such a benefit. In fact, there are techniques that can make the initial runs longer than the available internal memory. A more sophisticated merge sort that optimizes tape drive usage is the polyphase merge sort. Optimizing merge sort. On modern computers, locality of reference can be of paramount importance in software optimization, because multi-level memory hierarchies are used. Cache-aware versions of the merge sort algorithm, whose operations have been specifically chosen to minimize the movement of pages in and out of a machine's memory cache, have been proposed. For example, the tiled merge sort algorithm stops partitioning subarrays when subarrays of size S are reached, where S is the number of data items fitting into a CPU's cache. Each of these subarrays is sorted with an in-place sorting algorithm such as insertion sort. To discourage memory swaps, a normal merge sort is then completed in the standard recursive fashion. This algorithm has demonstrated better performance on machines that benefit from cache optimization. Cronrod suggested an alternative version of merge sort that uses constant additional space. This algorithm was later refined. Also, many applications of external sorting use a form of merge sorting where the input gets split up to a higher number of sublists, ideally to a number for which merging them still makes the currently processed set of pages fit into main memory. Parallel processing, merge sort parallelizes well due to use of the divide and conquer method. A parallel implementation is shown in pseudocode in the third edition of Corman, Lesserson, Rivest, and Stein's Introduction to Algorithms. This algorithm uses a parallel merge algorithm to not only parallelize the recursive division of the array, but also the merge operation. It performs well in practice when combined with a fast stable sequential sort, such as insertion sort, and a fast sequential merge as a base case for merging small arrays. Merge sort was one of the first sorting algorithms where optimal speedup was achieved, with Richard Cole using a clever subsampling algorithm to ensure O1 merge. Other sophisticated parallel sorting algorithms can achieve the same or better time bounds with a lower constant. For example, in 1991 David Powers described a parallelized quicksort that can operate in O, log n, time on a CRCW pram with n processors by performing partitioning implicitly. Powers further shows that a pipelined version of Batch's bitonic merge sort at O, log 2n, time on a butterfly sorting network is in practice actually faster than his O, log n, sorts on a pram, and he provides detailed discussion of the hidden overheads in comparison, radix and parallel sorting. Comparison with other sort algorithms, although heap sort has the same time bounds as merge sort, it requires only I1 auxiliary space instead of merge sort's I(n). On typical modern architectures, efficient quicksort implementations generally outperform merge sort for sorting RAM-based arrays. On the other hand, merge sort is a stable sort and is more efficient at handling slow-to-access sequential media. Merge sort is often the best choice for sorting a linked list. In this situation it is relatively easy to implement a merge sort in such a way that it requires only I1 extra space, and the slow random access performance of a linked list makes some other algorithms perform poorly, and others completely impossible. As of Perl 5.8, merge sort is its default sorting algorithm. In Java, the array sort methods use merge sort or a tuned quicksort depending on the data types, and for implementation efficiency switch to insertion sort when fewer than 7 array elements are being sorted. Python uses timsort, another tuned hybrid of merge sort and insertion sort, that has become the standard sort algorithm in Java SE7, on the Android platform, and in GNU Octave. Utility in online sorting, merge sort's merge operation is useful in online sorting, where the list to be sorted is received a piece at a time, instead of all at the beginning. In this application, we sort each new piece that is received using any sorting algorithm, and then merge it into our sorted list so far using the merge operation. Notes. References: Corman, Thomas H. Lesserson, Charles E., Revist, Ronald L., Stein, Clifford, 1990. Introduction to Algorithms. MIT Press and McGraw-Hill. ISBN A0-262-03384-4, Katarjanian, Zhki. Parzanin, Tomi. Tyler, Jukka. Practical in-place merge sort. Nordic Journal of Computing 3 ppA 27 €40. ISNA 1236-6064. Retrieved April 4, 2009 Also Practical in-place merge sort. Also, 1, Newth, Donald. Section 5.2.4, Sorting by Merging. Sorting and Searching. The Art of Computer Programming 3. Addison Wesley ppA 158 €168. ISBN A0-201-89685-0. Cronrod, M.A. Optimal Ordering Algorithm without Operational Field. Soviet Mathematics, Dokla D10. PA 744, Lamarca, A. Ladner, R.E. The Influence of Caches on the Performance of Sorting. Proc 8 An. ACM Siam Simp. On Discrete Algorithms, 370 €379 Sun Microsystems. Arrays API. Retrieved November 19, 2007 Sun Microsystems. Java Util Arrays Java. Retrieved November 19, 2007 External links, Animated Sorting Algorithms, Merge Sort a graphical demonstration and discussion of array-based merge sort, Dictionary of Algorithms and Data Structures, Merge sortiplet with level order recursive calls to help improve algorithm analysis, Open Data Structures, Section 11.1.1, Merge sort,